In this video, we're going to try to determine whether a series is absolutely convergent, conditionally convergent, or it's just flat out divergent. So a series we're going to test is the one on the left-hand side here, minus 1 to n of 5n plus 12 over 2n squared plus 3n plus 1. So whenever we're handed these problems out, absolutely convergent, conditionally convergent, divergent, the first thing we really ask ourselves is, actually, can we just use ratio test on this problem? And for ratio test, basically our series needs to have one of three types of functions inside of it in order to use it. In this case, we see we have no factorials inside of our series function. So if we're looking at our series function, there's no factorials there. We don't see any numbers raised to powers of n. So I'll just say numbers raised to powers of n. The only one we do see is this minus 1 to the n, but a minus 1 to the n isn't good enough for us to use ratio test for, as in we can't apply ratio test just because of a minus 1 to the n term. We need something like a 2 to the n, a 1/3 to the n, those types of things. And lastly, we don't see any n to the n terms. So because of this, ratio test is out in this problem. So what that means is, we're going to have to approach this absolutely convergent to conditionally convergent divergent problem the first way we've talked about, which is going back to what it really means to be absolutely convergent. Basically, take our series and look at the series with only positive terms in it by taking an absolute value of each term individually and determining whether that series converges. So we're really going to be looking at the following for absolute convergence. We're going to take our original series that we're given, but then throwing absolute value signs around each term, which results in basically the same series, but without the minus 1 to the n. So this series is full of only positive terms now. And for this series to be absolutely convergent, or original series to be absolutely convergent, we need to show that this series converges. So we're going to test this series on the right now for convergence. And if the series on the right converges, then the original series is absolutely convergent. All right, so how are we going to do this? Well, there's a number of series tests we could use. Things like, is this a geometric series? Do we use integral tests? Do we use comparison tests? All of those laundry list of series convergence, divergence tests. For this example, let's go back to some comparison tests. So for a comparison test, the first thing we need to do is find a series to compare to. So to do this, we take our series function that we are interested in. So in this case, it's the 5n plus 12 all over 2n squared plus 3n plus 1. And we basically ask ourselves, well, for large values of n, what terms contribute the most in the numerator and denominator? So looking in the numerator first, we have a 5n and we have a 12. And well, for very large values of n, that 5n is going to contribute the most in the numerator. So we put a 5n in the numerator on the right-hand side. And we do a similar thing for the denominator. We look at each of those terms in the denominator and ask ourselves, for large n, which term contributes the most? And well, it's going to be that 2n squared. So we can take that 2n squared and put it on the right-hand side. So it looks like the series function that we're going to compare to will be a 5 over 2 times a 1 over n after just doing a little bit of algebra. So we're going to compare to the following series. The series from n equals 1 to infinity of 5 over 2n. So we need to next see what this series that we're comparing to, what does it do? Does it converge? Does it diverge? So to do this, what we can do is, well, the series we're comparing to, we could take out a 5 over 2 in front, and then we have the series from n equals 1 to infinity of 1 over n. And remember, most of the time that we do this, we're always comparing to either a geometric series or a p series. In this case, this is a p series with p equals 1, which tells us it diverges. Also, we can see that this is actually the harmonic series. So we know it diverges as well. So now that we have the series that we're comparing to, we know what that series does. We have the option of doing one of two things for a comparison test. We could either try to set up an inequality and try to algebraically show that our series is greater than a known divergent series, because that's the only way we could guarantee something about our series when we're comparing to a known divergent series. Or what we could do instead is try to do the limit comparison test. So I just want to do the limit comparison test here just to practice some limits. So remember, for the limit comparison test, we take a limit as n goes to infinity of the ratio of our series functions, which in this case means we take the 5n plus 12, we divide by 2n squared plus 3n plus 1, and then we divide by the series that we're comparing to, the series of 5 over 2n. And now that we are taking a limit of a ratio of fractions, well, we can take that fraction in the denominator, we can reciprocate it and multiply it on. So we have the following. We have the 5n plus 12 all over the 2n squared plus 3n plus 1 times the reciprocal of that denominator, which is 2n all over 5. So we have to take this limit now for limit comparison. So let's just do a little bit of this distribution. So again, we're multiplying that 2n over 5 into the term on the left. So we multiply into both of these terms, the 5 into all three terms in the denominator. So we're taking the limit of what looks like 10n squared plus 24n in the numerator all over a 10n squared plus 15n plus 5 in the denominator. Now remember, for limit comparison test, what we want to show is that this limit is any finite non-zero number. If this limit is any finite non-zero number, then what limit comparison test tells us is both series do the same thing. So let's see what happens as n goes to infinity. Well, as n goes to infinity, this numerator is going off to infinity. And also as n goes to infinity, this denominator is also going off to infinity. So what this looks like for us is an infinity over infinity, an indeterminate form, so we can do L'Hopital's rule. So let's do L'Hopital's rule to help us with this limit. So we have the limit as n goes to infinity. Now taking a derivative of the numerator, we get a 20n plus 24. Taking a derivative of the denominator, we get a 20n plus 15. And now, after doing L'Hopital's once, we reevaluate that limit. So let's take a look at what happens in this numerator as n goes to infinity. As n goes to infinity, well, that 20n, that's going to infinity. In the denominator, again, that 20n is also going towards infinity as n goes to infinity. So again, we're in this infinity over infinity looking thing. So we have an indeterminate form that we can use L'Hopital's. So let's do L'Hopital's again. So taking the derivative of numerator again, in this case, we just get 20. In the denominator, we're taking the derivative, we get a 20. So this limit is the limit as n goes to infinity of 20 over 20. Or if we just simplify this, this is just the limit of 1 as n goes to infinity. And since 1 has no n's attached to it, this limit is just equal to 1. And now for limit comparison test, what I want to talk about is this is a finite and non-zero number. So what this means is a limit comparison test says both series do the same thing. Both series either converge or both series diverge. But if we go back up to one of those series, we know that one of those series, we know that it diverges. So we can combine these ideas. Limit comparison test says, hey, both series do the same thing. But since we know something about one of those series, as in one of those series diverges, using limit comparison test with that logic, both series must diverge. So going all the way back up into this problem, we did this whole comparison test, basically as a part of trying to determine whether a series was absolutely convergent. So the series we started with, we took the absolute value of each term individually, and then we just tested this series for convergence, and we found actually that series diverges. So going through all of that work, at this point, what we can say is original series is not absolutely convergent. So what does that mean now? Well, we showed the original series was not absolutely convergent, but we can move on next and determine whether the series is conditionally convergent. So let's go ahead and test for that next. And remember, the idea for conditionally convergent is basically saying that our series needs those both positive and negative terms in a specific arrangement in order to converge. That's what we're going to really be testing for here, is we're going to include the terms that are both positive and negative now and determine whether that series converges. So we're going to start off then with our original series. And we basically ask ourselves, what can we use to test this original series now? And the thing that's probably sticking out to you is this -1 to the n. And that -1 to the n is basically going to tell us, hey, you know what? We're going to be able to do alternating series test on this. Since basically what we see is this -1 to the n, that's responsible for all sign changes in this series, because this 5n plus 12 over 2n squared plus 3n plus 1, that was strictly positive. So let's use alternating series test. So for alternating series test, we first pick out the terms that are always positive in our series, or the terms that are not responsible for any sign changes. In this case, that is the 5n plus 12 all over the 2n squared plus 3n plus 1. And the reason for that is, for alternating series test, we need that this positive contribution of our series function satisfies two criteria, and then we can guarantee the series is convergent if it satisfies both of them. The first criteria is that when we take the limit as n goes to infinity of those positive pieces, that it equals 0. So let's test for this now. So again, we want to show that this hopefully equals 0. So we have the limit as n goes to infinity of the 5n plus 12 all over 2n squared plus 3n plus 1. So when we look at this as n goes to infinity in this limit, well, that numerator, the 5n plus 12, that n is going to infinity, so this numerator is looking like infinity. Similarly, this denominator as n goes to infinity, this denominator is also looking like infinity. So we have an infinity over infinity indeterminate form once again now in this problem. So we get to do L'Hopital's. So we have the limit as n goes to infinity. Taking the derivative of the numerator with respect to n, we just get 5. Taking the derivative of the denominator, we get a 4n plus 3. And now we reevaluate that limit. So again, this was our L'Hopital's step. We take the derivative of the numerator and denominator separately, basically to assess now, instead of the original numerator denominator, how fast they're growing. We take the rates of change of each individually to compare. So looking at this limit now, as n goes to infinity, well, that numerator, that's just a finite number. That's just 5. That denominator, though, this thing is still looking like infinity. So we have this situation of a finite fixed number all over a denominator. It's just getting larger and larger and larger. This thing equals 0. And again, for alternating series test, this was one of the criteria. We want to show that this limit does go to 0 of the positive stuff in our series function. So the second thing we do for alternating series is we show that everything is decreasing. And there's a couple ways we can show that these functions are decreasing. We can do this algebraically, or we can take a derivative of our series function that we have. So again, I'm going to define a function f of x, where I'm thinking of x now as any real number, or x greater than 1, I should say. But basically, we take our series function that with the positive terms only, as in the 5n plus 12 over 2n squared plus 3n plus 1. And anywhere there's an n, we really replace that with an x. The reason being, the original series function, n, is an integer that we're putting into it, whereas we're thinking about x as any real number. And in this case, we want x greater than 1, or greater than or equal to 1, really, because that is where our series starts and goes to infinity. Right? But what we want to show for this function to decrease is we want to show that its derivative is less than 0 for all x greater than or equal to 1, or at least after a finite x value and beyond. So let's go ahead and take this derivative. Before we take this derivative, I'm just going to rewrite this function in the following way. So I have 5x plus 12. Then I'm going to take this denominator and rewrite it as 2x squared plus 3x plus 1, all raised to the minus 1 power. And the reason for that is just so we can do a chain rule and product rule differentiation as opposed to a quotient rule. So taking the derivative now, we have the product of two things. We have the product of 5x plus 12, and then the product of the quantity 2x squared plus 3x plus 1 raised to the minus 1. So doing product rule, the first thing is we take the derivative of the first, which is derivative 5x plus 12. That's just giving us a 5. And then we leave that second term the same, 2x squared plus 3x plus 1 to the minus 1. And next we do the opposite. We leave the first term the same, 5x plus 12, and we differentiate that second term. So just slide this over to give us a little more room here. And now what you might notice is the second term, well, this whole quantity is raised to the minus 1 power. So we can do a power rule-like differentiation first. So bring that minus 1 down. And then we have the original thing, 2x squared plus 3x plus 1. Instead of being raised to the minus 1 power, we subtract 1 off of that, just like a power rule. So we have minus 2. But then we differentiate by the inside through the chain rule. So the derivative of the inside here is a 4x plus 3. So let's see what we get from this. We have this as f prime of x. We have this as 5 all over 2x squared plus 3x plus 1. Next we have plus, or actually a minus from this minus sign. We get a minus 5x plus 12 times a 4x plus 3 all over that denominator 2x squared plus 3x plus 1, that whole quantity squared. Again, that's taking this term and just using that minus 2 power. All right, well, this looks like a big old mess, but let's see what we have here. This is f prime of x equals, and what we can do is basically find common denominators here in order to combine these terms. So doing common denominators, you multiply this first fraction by, well, one other factor of what's in that denominator. So this is 2x squared plus 3x plus 1 to get common denominators. And now we can combine these things. So let's do this slowly here. We multiply this 5 and the 2x squared plus 3x plus 1. So we'll get from this term, we'll get a 10x squared plus 15x plus 1 minus, and let's distribute all of this stuff on the right-hand side. So 5x times 4x, that gives us 20x squared. 5x times 3 gives us a 15x. Now distributing the 12 into the next, we get 12 times 4x. That gives us plus 48x. And then finally, we have 12 times 3. That gives us plus 36. And that's all sitting on top of the same denominator now, which is the 2x squared plus 3x plus 1, that quantity squared. All right, let's see if we can combine anything. Well, the 15x and the 48x we can combine over here. And this gives us a 63x total. So now let's actually look at this numerator. All right, so we have a 10x squared. We're subtracting a 20x after we distribute that minus sign in. So we get a minus 20 or minus 10x squared. Next, we have this 15x, and we're going to subtract from it a 63x after we multiply it by, well, that minus 1. So we get is a minus 48x. And then finally, we have this plus 1. And after we multiply the minus sign in, or distribute that minus sign in to the plus 36, we have 1 minus 36. That gives us a minus 35. And that's all over that denominator. All right, now what we see is each of these terms in the numerator, they each have a minus sign attached to them. So let's just factor out that minus sign. We're almost done with proving that this is decreasing. So we factor out that minus sign, which means in the numerator now we have 10x squared plus 48x plus 35. In that denominator, we still have the same thing, the 2x squared plus 3x plus 1. And remember, what we want to talk about or try to show is that this derivative is less than 0 for any x values greater than 1. Okay? That was what we were trying to show, again, for this thing to be decreasing. And well, if we take a look at what we have, this denominator, whatever is in parentheses, we are squaring it. So that denominator overall, this thing's always going to be positive. This term in parentheses up here, well, this thing's always going to be positive. Again, because what we're asking about is for x values greater than or equal to 1. So the only thing that's contributing a minus sign is this minus sign in front. So we always have minus some positive number. So this derivative is indeed less than 0 for x values greater than or equal to 1. So the second criteria for alternating series test is finally satisfied, and we've shown this. So by alternating series test, we show that our series is convergent. And remember, what we did in the grand scheme of things here is we were testing for conditional convergence. So we took the original series we were handed, this one even on the left-hand side, we kept those -1 to the ends in there and tested that series for convergence. So since this series now converges, we know that it's actually conditionally convergent. So our original series is conditionally convergent. And what that means is, well, the series, in order to converge, needs those minus signs, or needs both positive and negative terms in a particular arrangement to guarantee convergence. So we just showed this series was conditionally convergent, because when we tried to show that it's absolutely convergent, we saw that it's not absolutely convergent. So then we went and tested for conditional convergence, which led us down this alternating series test. And because we found that the original series then was convergent using alternating series test, it must be conditionally convergent.